A lightning strike releases tens of thousands of amperes in a fraction of a second. It is a chaotic, disastrous equalization of charge between the atmosphere and the Earth. But when that same flow of electrons is controlled, moving smoothly and steadily like water in a river, it powers the modern world. We define this controlled flow mathematically. Electric current is simply the net amount of charge that passes through a specific cross-sectional area over a given time interval. To see how that happens, we have to look inside a solid metallic conductor. The structure consists of a rigid background of fixed positive ions, completely permeated by freely moving, negatively charged electrons. Under normal conditions, these electrons move in entirely random directions. For every electron moving right, another moves left. The net flow is zero. The electric current is zero. To create a directional flow, imagine attaching a positively charged disk to one end of a metallic cylinder and a negatively charged disk to the other. These create an electric field through the cylinder, forcing free electrons to drift toward the positive end. If we continuously replenish the charges on the disks, we maintain a steady, forward-drifting net flow. We measure this flow in amperes. An ampere is defined as 1 coulomb of charge passing through the area per second. An external electric field imposes order on microscopic chaos to create a current, but the physical material of the cylinder itself naturally resists this flow. Zooming back out to the macroscopic scale, we can observe exactly how different materials restrict this flow in standard electrical circuits. In 1828, the German physicist Georg Simon Ohm figured out the mechanics of this restriction. He was actually guided by studying the conduction of heat, realizing that an electric field pushes current very much like a temperature gradient pushes heat. Ohm observed that the current flowing through a conductor is directly proportional to the potential difference, or voltage, applied across its ends. Double the voltage, and the current doubles. This schematic shows the relationship in action. As the voltage meter rises, the current meter rises linearly. The constant of proportionality linking them is resistance, measured in ohms. This gives us the equation voltage equals current times resistance, or V equals IR. Resistance is a property of the object itself. It tells us exactly how much voltage is required to push a specific amount of current through that particular object. But resistance is not a universal constant for a material. A copper wire will have a completely different resistance depending on how long it is or how thick it is. V equals IR describes a specific object in a specific shape. To understand the true electrical identity of the metal itself, we have to mathematically strip away its physical dimensions. We can isolate the geometry from the material using a brief thought experiment. We will start with a single rectangular slab of conductive material. It has a length of L and a cross-sectional area of A. We apply a voltage V across its ends, and a current flows through it. The resistance of this single block is V divided by I. Now, place a second identical slab side by side with the first. The total length of this new combination is 2L. Because these slabs are locked in a sequence, the exact same current I must travel entirely through the first block and then entirely through the second block. The potential difference across the ends of the first slab is V. The potential difference across the second is also V. So the potential difference across the entire combined length is 2V. To find the resistance of the combination, we divide the total voltage, 2V, by the current, I. Because V over I equals our original resistance, the total is exactly 2R. Doubling the length of the conductor exactly doubles the total resistance. The charges have to traverse twice as much physical material, encountering twice as many obstacles. Resistance is directly proportional to length. Now we return to our single slab to test the second dimension. Imagine dividing it lengthwise into two identical halves. Look at one of these half slabs. It still has the original length, L, but its cross-sectional area is exactly halved, A divided by 2. If we apply the same total voltage V across the ends, the original current splits between the two pathways. The current flowing through our specific half slab is only I divided by 2. We calculate the resistance of this thinner slab by dividing the voltage, V, by the reduced current, I over 2. The fraction flips, giving us 2 times V over I. The resistance is exactly 2R. Having the cross-sectional area exactly doubles the resistance. We now have our two geometric rules. Resistance is directly proportional to length and inversely proportional to area. We combine them to state that resistance is proportional to L over A. To make this an equal sign, we introduce a constant of proportionality. The equation becomes R equals rho times L over A. Rho is a property called resistivity. Resistivity is the intrinsic electrical identity of the material itself. A solid block of copper and a thin wire of copper have wildly different resistances, but they share the exact same resistivity. By isolating the physical bulk variables of length and area, we have successfully extracted the pure material property. We can now look at how conduction works at a precise microscopic point. We leave the macroscopic wire behind. We are now looking at an infinitesimal coordinate point inside the lattice of the material. Down here, macroscopic voltage and current don't apply. We redefine our variables. Voltage divided by length is the local electric field, E. Current divided by cross-sectional area is current density, J, the charge flowing through a unit area normal to the flow. We can substitute these microscopic vector properties directly back into our macroscopic equation, V equals I times rho L over A. We substitute these in. V equals electric field times length, and I equals current density times area. E times L equals J times A times rho L over A. The area cancels out on the right. The length is on both sides, so it cancels too. The physical dimensions vanish completely. We are left with the microscopic form of Ohm's law. E equals J times rho. This is a universal statement about vector fields. A local electric field generates a directly proportional local flow of charge density. The single variable determining the scale of that flow is the resistivity. To understand where resistivity comes from, we look at the physical mechanics of the lattice. When an electric field is applied, electrons experience a force, but they do not accelerate indefinitely. They constantly crash into the fixed, heavy positive ions of the metal, deflecting randomly with every collision. Despite chaotic bouncing, the electric field ensures they make slow, continuous progress in one direction. We call this net forward speed the drift velocity. This chart shows the resistivity of a typical metal as a function of temperature. As the metal gets hotter, the internal atoms vibrate more violently. The electrons suffer more frequent collisions, slowing their drift velocity and increasing the overall resistivity. The macroscopic resistance of a wire is just the cumulative, macroscopic measurement of trillions of these microscopic atomic traffic jams. Ohm's law perfectly describes this linear relationship between the field and the flow in standard metals. But it is an empirical observation, not a fundamental law of nature. Many materials completely violate this proportionality, especially when the applied electric field becomes too strong. This graph shows the behavior of a semiconductor. Unlike copper or iron, the resistivity of a semiconductor rapidly decreases as the temperature goes up. We engineer devices specifically to break Ohm's law. A diode restricts current to a single direction, meaning current depends entirely on the voltage sign. Materials like gallium arsenide have non-unique relationships, where one current value occurs at multiple voltages. While passive wires strictly obey Ohm's law, modern computing and electronics are built almost entirely on the devices that break it. But you cannot manipulate the nonlinear exceptions until you understand the baseline. Isolating the geometry of a wire to reveal the pure vector mechanics of Ohm's law is the foundation of controlling the flow of energy.